Okay, let's jump right into this. So picture this. It's handover day on your site. The cable trays look perfectly aligned, the client is smiling, the place is clean, and honestly, everything seems rock solid. But here is the hard truth I've learned from years out in the field. The real test of a structural installation, it doesn't actually happen when you cut the ribbon. It happens months down the line. So why do systems that look absolutely perfect on day one suddenly start to sag, vibrate, or even completely collapse 6 months later? Well, that is exactly the critical engineering question we're answering today.
Welcome to today's Explainer. Think of this as your senior engineer's technical briefing. We are going to unpack a totally field-tested framework for cable tray support selection. Because, look, in our line of work, hope is not a strategy. We need absolute certainty to prevent expensive and, frankly, dangerous structural failures. I'm going to walk you through the precise logic and the exact math you need to get this right, every single time.
Here is our roadmap for today. First, the post-handover crisis. Second, span, deflection, and math. Third, the 5 support types. Fourth, hidden loads often missed. Fifth, the 5-step selection workflow. And finally, number 6, Xinma quality and standards. Let's get to work.
All right, section 1, the post-handover crisis. We really need to expose the dangerous trap of the good enough installation. You see, cable tree support is the exact thing that turns a passive cable management system into a predictable load-bearing element. If you get the span, the load class, or the support type wrong, well, you've just turned a reliable system into a massive liability. Gravity and time, they will always expose your shortcuts. The real consequences, things like deflection, excessive vibration, and aggressive corrosion, they don't usually announce themselves immediately. They creep in quietly, just degrading the integrity of the infrastructure long after you've packed up your tools and left the site.
Moving on to section 2, span, deflection, and math.
Let's look at the hard physics of this. Say you have a standard 2.0 meter span versus a 4.0 meter span. Look, we've all felt the temptation on site. You're behind schedule, materials are running tight, and someone says, hey, let's just double the distance between the supports to 4.0 meters. I mean, the tray looks stiff enough, right? It saves a little time, maybe saves a few brackets. But as any veteran engineer will tell you, structural integrity isn't about guessing. It's about unforgiving math. Structurally, what are you actually doing to the system when you stretch that span?
The critical number you absolutely have to burn into your brain is 16x. Doubling the span from 2.0 meters to 4.0 meters doesn't just double the sag. Because of the way bending moments work in structural mechanics, doubling your span causes a massive 16-fold increase in deflection. Just think about what a 16 times increase in sagging does to your cable weights, your joints, and your structural anchors. This right here is the wake-up call. Real project spacing decisions absolutely must be driven by this math, not by installation convenience.
Section 3, the 5 support types. Now that we respect the math, let's open up the toolkit. We've got 5 main types to work with: wall brackets, ceiling hangers, floor racks, trapezes, and beam clamps. And here's the thing, you cannot just pick whatever happens to be rolling around in the back of the truck. A ceiling hanger is completely useless if your overhead structure can't take the tension. A wall bracket fails if the masonry is weak. Now, trapezes are fantastic for heavy multi-tier runs, while beam clamps let you tie directly into the primary steel without any drilling. You only achieve a predictable load-bearing element when you match the specific support type to the exact structural environment of your site.
Section 4, hidden loads often missed.
These are the dynamic hidden loads that rookies almost always forget to calculate, completely invalidating their load math. First up, future cable allowance. Listen, someone will invariably pull more cables next year. It's just a fact. If you didn't leave a 20 to 30% structural capacity for that, the system fails. Second, covers. They add dead weight and they totally change wind loading if you're outside. Third are point loads. Think of a heavy junction box or, someone resting a heavy ladder on the tray. And lastly, seismic acceleration. In an earthquake, the static weight of your cables multiplies dynamically. If you haven't engineered for these hidden loads, you really haven't engineered the support at all.
Section 5, the 5-step selection workflow. To prevent those rookie mistakes and guarantee the math actually works, here is the exact reproducible workflow that will literally save your site. Step 1 is route mapping. You have to understand the physical pathway and structural tie-in points before you do anything else. From there, step 2, you calculate your total loads, including all those hidden ones we just talked about. Step 3, you dictate your optimal span to avoid that 16 by deflection trap. Next, step 4, you select from our matrix of the 5 support types based on your environment. And finally, step 5 is corrosion and fire coordination. You have to ensure your brackets and anchors won't rust out in a damp environment or fail prematurely in a fire rating zone. This workflow is what guides you safely from a blank blueprint all the way to a certified installation.
Section 6, Xinma Quality and Standards.
An engineered blueprint is honestly only as good as the physical components you use to build it in the real world. When you're dealing with high-stakes environments, we're talking data centers, rail transit, industrial plants, and massive commercial buildings, you simply cannot rely on generic hardware. As a senior engineer, I'm always looking for comprehensive, seamless systems like those from Xinma. Whether it's cable tray systems, busways, dedicated seismic bracing, or intelligent cable management. Look, if you are calculating for seismic acceleration, you need a manufacturer that provides specialized seismic bracing that plays perfectly with their cable trays.
But here's the absolute most important part of selecting your components: strict compliance. Our industry relies on absolute certainty, utilizing components from Xinma that meet rigorous global standards like IEC 61537, NEMA VE1, BSEN 50085, and GB 31251. That is completely non-negotiable. These standards guarantee that the steel thickness, the load ratings, and the corrosion resistance perfectly match the unforgiving math you just did. When the standard says the bracket will hold, it holds.
Which brings us to our final takeaway today. I want you to think about this. Are your current support spans mathematically safe, or are you kind of just guessing? I challenge you to go back to your current job sites tomorrow with a highly critical eye. Look at the brackets. Look at the distances. Remember that 16-fold deflection trap? Verify that your installations are backed by solid engineering, the right support types, and globally compliant materials. Because doing it right the first time, that is exactly what separates the rookies from the veterans. Thanks for joining me on this explainer, and stay safe out there on site.